Hello everybody. We were discussing about this canonical form of second order linear partial differential equation. Hmm? And there I introduced two transformation like xi is equal to xi of xy and eta is equal to eta of xy, so that the Jacobian of the transformation is not equal to 0. And here a partial differential equation, like this kind of partial differential equation, this kind of partial differential equation under the transformation, ultimately it converts into a partial differential equation like this, where these are the coefficients. These are the coefficients: a bar, b bar, c bar, d bar, e bar, and a bar, g bar. These are the coefficients in this partial differential equation. And I introduced the canonical forms, that this kind of either this first form or the second form, whatever form you consider, this is called the hyperbolic partial differential equation. Then this one is called the elliptic partial differential equation, and either u xi is equal to some function, or u eta is equal to some function. This is called the parabolic differential equation. And we can establish this kind of relation, that b square minus 4 b bar square minus 4 a bar c bar, that is actually is equal to this Jacobian of the transformation j square into b square minus 4ac. It can be proved that this relation holds. Now today I am going to discuss the canonical form of hyperbolic equations, and I shall discuss an example, and if time permits I will try to discuss the canonical forms of parabolic equation as well. Over here you see we need to determine the transformation formula. This transformation formula, xi is equal to xi of x comma y, and eta is equal to eta of x comma y. We need to determine this kind of transformation formula. We shall be given a partial differential equation, a linear second order partial differential equation, and from that differential equation we need to consider these two transformation. How do we consider this transformation, that I am going to discuss during this course, during this lecture. And there we have two independent quantities, xi and eta. Not independent, they should be dependent on x and y. But if you consider xi and eta, we need to choose two functions, and these two functions, xi and eta. So that can be done if we can impose two conditions on the relations involving xi and eta. You see, we already have this type of relation over here. These are the relations, a bar, the expressions of a bar, b bar, and all. So now if we can impose this kind of relation, this is equal to 0 and this is equal to 0. We don't know whether this kind of imposition or this kind of assumption is valid or not. Our target is to consider this kind of transformation, so that this a bar becomes is equal to 0 and this c bar becomes is equal to 0. If it is possible, we don't know whether it is possible or not. Let's see. We shall check. If it is possible to choose xi and eta in such a manner, then that this is equal to 0 and this c bar is equal to 0. then what would be its consequences? Let's check the consequences. You see, this is the expression of a bar and c bar if these are equal to 0. Then we can divide these relations. We can divide this first relation by xi partial derivative xi y. And we can divide this second relation by partial derivative eta y. Okay, so after division we have this type of relation. This is equal to 0 and this is equal to 0. You see, this xi x by xi y, this first relation is actually a second degree equation in this kind of expression xi x by xi y. So if we solve this relation, we would get certain we would get two different values of this expression xi x divided by xi y. Similarly, if we solve this second relation, we will have two different expressions of eta x by eta y. And if you look at this carefully, that xi x and xi y, both of them, this ratio is equal to minus b plus minus root over of b square minus 4ac divided by twice. Even if you solve this relation, in that case also you would get the expression xi x by eta x by eta y is equal to this same expression. So whenever you solve these two relations, you are ultimately going to get same roots. So we can consider any one symbol, say positive symbol, for the value of xi x by xi y, and then we can consider this negative symbol in order to consider the value of this eta x by eta y. You can consider any two symbols. So over here, this positive symbol, the positive sign is taken in order to choose the expression of this xi x by xi y, and negative symbol, this negative sign is chosen in order to consider the expression of eta x by eta y. You can choose different expressions as well. You can choose negative value over here, positive value over here, it doesn't matter. Anyway, it would be certain numerical value. The right hand side expressions would be certain numerical values. Now you see, from this relation what we observe. You see, if you consider this kind of relation xi x comma y, but this was the dependent variable xi. I am considering the functional expression xi of x comma y is equal to, suppose, certain constant c1. Then what would happen if we differentiate this relation? If we differentiate this relation with respect to x, or you can say we can also consider the differential, then you see this d of xi would be is equal to 0, and that differential will give us the relation that del xi del x, or partial derivative xi x into dx plus del xi del y, or partial derivative xi y dy is equal to 0. And from this relation we can say that dy dx with a negative symbol, that expression would be is equal to how much? Xi x xi y. So you see, this dy dx will be equal to xi x by xi y, and in that case this xi x by xi y, this becomes is equal to certain dy dx. What is dy dx? Dy dx is actually the gradient of some curves. Say if this curve chi of x comma y is equal to c1, if this is the curve in the two-dimensional plane, then might be at certain point this dy dx will ultimately give us the direction of certain tangent. Similarly, for the second curve, if for the second eta, if you consider the relation that eta of x comma y is equal to suppose c2, in that case this expression can be deduced from the relation eta of xy is equal to this c2, and that quantity, this eta y eta x by eta y will again be certain dy dx like expression. So we can say that this expression, the first expression, gives us the gradient of the tangent maybe is equal to m1, and the second expression gives us the gradient of the tangent of this kind of curve eta x comma y is equal to c2. So suppose this is the second curve, and this might be the direction of the tangent here. So what we observe over here geometrically, what we observe that this kind of relation, will give us two such expressions. Xi of x comma y is equal to c1, and eta of x comma y is equal to c2, and from that relations you see we can identify the functional form of xi and eta. Okay, from that relation we can identify the functional form of xi and eta. So that was our target. You see, we wanted to identify this kind of expressions. We wanted to identify the expressions of xi and eta. We did not know what was the expression of xi and eta. So by just putting capital A bar is equal to 0 and capital B bar is equal to 0. Why did we put capital A bar is equal to 0, capital B bar equal to 0? Because of two reasons. The reason was that we could impose two conditions so that we can determine these two unknown functions. And by mathematical manipulation, if we integrate this relation, we would be able to determine this kind of xi and this kind of eta. Secondly, if we put a bar is equal to 0 and b bar is equal to 0, then you see, you consider this expression b square may be not equal to 0, but if a bar is equal to 0 and c bar is equal to 0, then the total expression, this expression b bar square, is b bar square minus 4 a bar c bar. This simply becomes is equal to b bar square, and this becomes always greater than 0, so that the this relation b square minus 4ac, this kind of relation greater than 0 is satisfied. That means we can easily set a bar is equal to 0 and c bar is equal to 0 and determine the expressions of xi and eta from the given differential equation. So that was our target, and this kind of relation xi and eta, these relations xi and eta, these are actually called the characteristic equations. These are actually called the characteristics equation. This one, characteristic equations. So that along these two directions, along these two direction, if you consider the transformation, maybe this is the direction of chi, and maybe this is the direction of eta. So along this direction, if you choose the coordinate axis, in that case with respect to these two coordinate axis, or with respect to these two coordinates, the given partial differential equation is converted into the canonical form of the hyperbolic partial differential equation. That is the basic idea over here. Let's move to an example. Let's move to an example. If you look at this example, 3uxx plus 10uxy plus 3uyy. Now compare this equation with the standard standard form, the given form of a partial differential equation. What was the form? Let us recall this form. Equation number 1.4. Equation number 1.4 was this one. This was the equation number 1.4. So over here, this capital A is actually the coefficient of uxx, then capital B is the coefficient of uyy, and capital C is the coefficient, capital B is the coefficient of uxy, the mixed partial derivative, and capital C is the coefficient of uyy. And in the given question, D is equal to 0, E was equal to 0, F was equal to 0, and G was also equal to 0. So these were the relations. Now let's move to the differential equation. The example. This was the example. So over here, this uxx, the coefficient of uxx, that is A is equal to 3. The coefficient of uxy, this is our B is equal to 10, and coefficient of uyy, that is our C. So C is equal to 3, and the remaining expressions D, E, F, G, all these expressions are equal to 0. So we can say that D is equal to E, that is equal to F, and G, all these quantities are equal to 0. Anyway, over here, b square minus 4ac, that is equal to 64, is positive, a positive quantity. Therefore, we can conclude that this given partial differential equation is a hyperbolic partial differential equation. Okay. Now, we already got the expression of chi x and chi x by chi y, and we got the expression of eta x by eta y. So in that expression, if you put these values of a, b, and c, if you put the values of a, b, and c, then we will be able to compute dy dx from the first ratio and dy dx from the second ratio. So over here, dy dx from the first ratio is equal to 1 by 3, and dy dx from the second ratio, that is equal to 3. Now, if we integrate, or you can write it this expression in this way, that 3 into dy is equal to, or minus dx is equal to 0. Now if we integrate this one, what we have? We shall have 3y minus x is equal to certain constant, maybe is equal to c1. And I told you that what was the chi? Chi is equal to constant should be obtained from this relation. So we can say that this is the function chi of x comma y. So how chi looks? Chi looks in this fashion, that chi is equal to 3y minus x. So in this fashion, we can determine the expression of chi. And similarly, if we consider this second partial differential equation, this second partial differential equation can be written as 3dx minus y is equal to c2. So that if we integrate them, after integration, what we have 3x minus y is, sorry, not c2. Over here this should be is equal to 0. Differential dy. After integration, what we get 3x minus y is equal to some arbitrary constant c2, and you can now choose this one to be is equal to the function eta of x comma y. So this eta, we can now choose this eta as equal to 3x minus y, and xi is equal to 3y minus x. So in this fashion, we can determine the expressions of xi and eta. Now, once you determine the expression of xi and eta, you can compute the higher order derivatives. Over here, you see, over here in this expression, you see in this expression a bar should be is equal to 0, fine, and c bar would be is equal to 0. Now, if you know the expression of xi and eta, then you can easily compute these partial derivatives, xi x, eta y, xi y, eta x, and all. Then you can compute the expression of b bar. Similarly, you can compute the expression of d bar, e bar, etc. So in this way, you can compute the remaining expressions, and afterwards, you see this is the expression xi is equal to y minus 3x. And what was eta? Over here, I have taken eta is equal to 3x minus y, because we got the relation after integration, this kind of relation. You could also divide it by 3, because over here it is also permissible to divide it by 3, so that ultimately after division it will have this kind of relation, eta is equal to x minus y by 3. It doesn't matter, is equal to some constant, arbitrary constant c2. So they have taken eta is equal to x minus. You can also adjust the positive or negative sign over here, because over here on the right hand side we have 0. So you can simply consider the positive sign or the negative sign as well. In that case, it would be eta would be is equal to y by 3 minus x. Y minus x by 3. So in this way, it would be the expression of eta. You can choose different expressions of eta, either x minus 3y or y minus 1 by 3x, whatever you want to consider. So you need to choose, you need to obtain the expressions of this xi and eta, and there you can, after computation, you can easily find out the expression of this b bar and c bar and all. And if you just put these expressions in the canonical form, what we get, you see over here, a bar is equal to 0, c bar is equal to this c bar is equal to 0, and the remaining expressions are all equal to 0. Only the contribution from b bar would come. Over here, b bar is equal to minus 64 by 3. So what was the canonical form? Finally the contribution from b bar should come. So b bar into what we have, the dependent variable was u. So u of partial derivative xi and eta, that would be is equal to 0. So this is the expression over here. This is the expression. And therefore, if you cancel the 64 by 3, we have this kind of relation, u of xi eta is equal to 0. Now you can stop over here. You can stop your computation in whenever you get this kind of canonical form. But this is a very easy canonical form, and this is easy to integrate, so you can further integrate it. You see, once we integrate it with respect to eta, if we integrate it, if we under integration, after integration, what we get, suppose you are integrating at first with respect to maybe eta, then after integration, what we have, we shall have u xi is equal to maybe some quantity which does not depend upon eta. All right, it may be certain quantity which does not depend upon eta, because that would ultimately, after differentiation, will lead us to this kind of partial derivative. So let us write it as certain expression, or you can say certain function involving xi. You see, if we differentiate this expression further with respect to eta, then after partial differentiation with respect to eta, the right hand side will become equal to 0, and on the left hand side we will have u xi comma and xi eta is equal to 0. So we can say that whenever we integrate it with respect to eta, we will get certain arbitrary function not involving eta. It may involve other quantities. So we can say that this is an arbitrary function. And over here we have just simply considered a. So let us write it as a. Okay, you can write f1, it doesn't matter. Now if we want to integrate it with respect to this xi, in that case, after integration again, what we have, we shall have u is equal to, that would be the integral of this function f1 with respect to this xi plus certain quantity which does not depend upon this xi. So let's write it as, it may depend upon eta, so let's write it as g of eta, and this expression, this integral of f1, this integral has been written as f of xi. That would also be a function of xi. Got it? So finally we shall have this type of relation, that u is equal to some function of xi plus some function of eta. F and g, these are some arbitrary functions of xi and eta. Now we have the expression of xi, so we put xi is equal to y minus 1 by 3, y minus 3x, and we know the expression of eta, so we put eta is equal to y minus x by 3. So in this fashion you can compute the solution, of the partial differential equation represented in canonical form. Got it? But so always this kind of solution is not easy to find. Over here the canonical form was very easy, that's why we were able to find out this kind of solution of the given differential equation. But most of the times this solution is not easy to find. So if it is not easy to find, you have to stop in this level. Let's move to the parabolic differential equation. Now, in case of parabolic differential equation, the condition for parabolic differential equation is that b square minus 4 a bar c bar is equal to 0. And if it is 0, then from this relation, you already have this relation that this is equal to the Jacobian j square multiplied by b square minus 4ac. So this expression would also be equal to 0 in case of parabolic partial differential equation. So let's discuss the canonical form of parabolic partial differential equation. Now in parabolic partial differential equation, you see, if this suppose if this is equal to 0, b square minus 4 a bar c bar is equal to 0, what does it mean? B square minus 4 a bar c bar is equal to 0. It means that b square, this b square is equal to 4 a bar c bar. So this is b square, b bar square, b bar square, b bar square. And if a bar is equal to 0, then b bar becomes is equal to 0. We can mathematically prove all these results because everything, all these computations have also been demonstrated over here, that if a bar becomes is equal to 0, then this b bar, this expression ultimately becomes is equal to 0. I am not going through the all these complicated computations. Okay. So from the common sense, it is clear that if a bar is equal to 0, then b bar would always be equal to 0. You could also take c bar is equal to 0, even then this b bar becomes is equal to 0. So it is not required to always consider a bar and c bar both equal to 0. If you consider this expression is equal to 0, in that case this b bar becomes is equal to 0. This much we can say. So from this result we can say that if say if this a bar becomes is equal to 0, then this b bar is also is equal to 0. Or we can also say, or if c bar, this c bar is equal to 0, then b bar is equal to. So we actually have only one relation, a bar is equal to 0 or c bar is equal to 0. Only one relation will give us the result that b bar square minus 4 a bar c bar is equal to 0, and from that relation we can have the result that b bar is equal to 0. So we can choose only one relation. Either we can choose a bar is equal to 0 or we can choose c bar is equal to 0. So let us for the sake of discussion we choose a bar is equal to 0. So what we have, we actually imposed only one relation. We actually imposed only one relation, a bar is equal to 0, and we expect that from this relation we will be able to compute the relation like xi of x comma y is equal to maybe some constant c1. And from that relation we will be able to compute the expression or the functional form of xi. Now the question is that how can we take the expression of this eta? Got it? I am coming to the discussion because we will have to impose or we will have to use our intelligence, and that would come from practicing different or solving different partial differential equation. So we will have to choose another expression of eta from our experience, so that this xi and eta becomes independent of each other. Okay, we can choose the expression of xi, or we can obtain the expression of xi if we impose this condition a bar is equal to 0. But from that relation we will be able to choose only the expression of xi. Similarly, if we put c bar is equal to 0, we will be able to compute the expression of eta only. So in this case, the problem is that we are able to compute the expression of xi or expression of eta, only one expression, and second variable has to be chosen from our common sense. Alright, so that this xi and eta is independent of each other and this Jacobian is not equal to 0. All these conditions are satisfied. So let's rather discuss over here without going to this complicated computation, let's rather discuss an example over here that would make our process a bit easier to understand. So let's consider this kind of partial differential equation over here. Say x square u xx minus twice xy u xy plus y square u yy is equal to e to the power of x. So over here the right hand side was equal to g, and this coefficient x square, this was the quantity, the coefficient capital A, minus twice xy, this would be the quantity capital B or the coefficient capital B, and similarly over here y square, this would be the coefficient capital C. So from the expressions of capital A, B and C, we got the expression that b square minus 4ac becomes is equal to 0. So we can conclude that yes, the partial differential equation is a parabolic partial differential equation. Now you see, if you look at the old computation there, if a bar is equal to 0, so from that relation we got the expressions of chi x by chi y. Now over here, in case of parabolic partial differential equation, this b square minus 4ac becomes is equal to 0 in case of parabolic partial differential equation. So this expression becomes is equal to 0, the expression within this root, and therefore in case of parabolic partial differential equation, this expression will be is equal to simply b divided by twice, okay, minus b divided by twice. So that's why we have in this example, we have directly written that chi, over here you see, chi x by chi y is equal to minus b divided by twice a, and therefore if we adjust this minus sign over here, it would be minus chi x by chi y, that is equal to b by twice a. So this is the expression we have from the relation that a bar is equal to 0. And from this relation we can compute the expression of dy dx. Ultimately by computation, this dy dx becomes is equal to y by x, and so we can write dy divided by y plus this dx divided by x is equal to 0 and 0. And after integration it would be xy is equal to some constant, maybe c1. So we can choose this expression to be is equal to the function chi, or we can say that this chi of x comma y, that is actually is equal to our x into y. So this is the expression of chi. So in this way we got the expression of chi. Chi is equal to x1. If you consider these examples, you got the expression of chi, that chi is equal to this x1. Now how to choose eta? The second problem, how to choose eta? From experience one can say that if we choose eta is equal to y, then you can check that the Jacobian will be not equal to 0. What was the Jacobian? The Jacobian was that chi x eta y minus eta y chi x. You can check over here that if suppose this chi is equal to xy and eta is equal to y, then from this relation what we can say, that the Jacobian j is equal to the partial derivative chi x. Partial derivative chi x means that is equal to y into eta y. Eta is equal to y, so partial derivative eta y, it means 1 minus chi y. The partial derivative chi y, is equal to x into this eta x. Now what was eta? Eta is equal to y, therefore eta x, that would be is equal to 0. So ultimately this expression is equal to y, and we can say that this is not identically equal to 0. Therefore what you observe is that this is a valid choice. Eta is equal to y is a valid choice with xi is equal to xy, so that this Jacobian is not equal to 0. Here, so in this way we can choose eta is equal to y. So in this fashion we can choose the expressions of xi and eta, and ultimately again by previous technique we can compute the we can find that a bar, this a bar becomes equal to 0 and b bar is equal to 0, and of course in that case we would get c bar is not equal to 0. We got c bar is equal to y square, and similarly the remaining portion, the d bar, then g bar, etc., we got the remaining coefficients. So if we put these coefficients over here, you see a is equal to 0 and a bar and b bar both are equal to 0, so no coefficient involving a bar and b bar would appear. We will have certain coefficient like c bar into u xi, sorry, not xi, eta, because c bar was the coefficient of u eta, plus d bar into u xi, because over here d bar is not equal to 0. Then e bar and f bar both becomes is equal to 0, and on the right hand side we have this g bar. So this gives us this type of relation that c is equal to y square into u eta, and then d bar is equal to minus twice xy, so this is minus twice xy into u xi, and on the right hand side this is the expression of g bar. So if you put y square, what is y was taken to be is equal to eta, so everything has to be converted into xi and eta. So y square is being written as this eta square, and what was xi? Xi was equal to x into y. Therefore this xy, this expression xy has to be converted into this xi. All right, and e to the power of x, if y is equal to eta and xi is equal to xy, so from this relation we can say that x would be is equal to this kind of expression xy divided by y. That therefore x would be is equal to this xi divided by eta. So that's why in place of this x we have the expression of this xi by eta. Got it? So in this way we will be able to compute the expression of x, and you see in the computation of expression of x depends upon the expression of this xi is equal to eta. So if we choose this kind of easy expression xi is equal to eta, in that case the computation of x becomes much more easier. Otherwise it would become a bit complicated. So that is the second information that I wanted to highlight. So anyway, so this is the canonical form, because of the fact that you see on we have u eta. U eta is equal to the remaining functional expressions involving the first order partial derivatives and other functions. So this is the canonical form of the given parabolic partial differential equation. So in this way you will have to convert the given equation into the parabolic partial differential equation like this. It is not always easy to solve, so you don't need to solve all these partial differential equations. Most of the times you will be given to convert or you will be given to compute the expressions of xi and eta, because these are the canonical equations. And by the help of this kind of canonical transformation of canonical equations, you will have to convert them into the canonical form. This much will be given as the question in your exams. It is not always easy to solve them. That's why the conversion of a given partial differential equation into canonical form, that is the most important problem over here. And there are other standard different techniques by which we can solve them, that we shall discuss accordingly later on in the future lectures as per the syllabus. Okay, so that's all for today's lecture.
সো আমরা যদি ইটাটা আমরা নিজে চুজ করলাম, যদি ডিফারেন্ট ইটা চুজ করি তাহলে যে ক্যানোনিক্যাল ফর্ম যেটা আসছে মানে যেটা আমরা সরি ট্রান্সফর্মড ইকুয়েশন যেটা পেলাম ওটা কি ডিফারেন্ট আসবে?
হ্যাঁ, আসতে পারে। তার কারণটা ক্যানোনিক্যাল ফর্মটা এখানে কিভাবে আমরা ইটা ইজ ইকুয়াল টু ওয়াই চুজ করছি, সেখান থেকে এই জায়গাটা ক্যানোনিক্যাল ফর্ম চেক হচ্ছে। তো ক্যানোনিক্যাল ফর্মে এই যে কোএফিসিয়েন্ট গুলো আলাদা আসতে পারে ইন দ্যাট কেস। ক্যানোনিক্যাল ফর্মটা হয়তো চেঞ্জ হবে না, বিকজ প্যারাবোলিক ইকুয়েশন প্যারাবোলিকই থাকবে, শুধু এখানে যে কোএফিসিয়েন্ট গুলো আছে কোএফিসিয়েন্ট গুলো ইন দ্যাট কেস আলাদা আসতে পারে।
আচ্ছা হ্যাঁ স্যার বুঝছি।
So that's all for this lecture. Thank you for being with us.